Hi everybody, welcome. Lovely to see all of you, although of course I can't actually see your faces. Do say hi in the chat. Very exciting to be here. I am kind of taking over from Nevin, who I believe is usually the program manager for the Educate to run this session. And it is my pleasure to introduce Dieter Sommer, who will be giving us a technical dive into Chain Fusion. Now, hopefully he is here and I will be able to invite him to the stage. I think that should be working and he should pop up on your screens in just a moment, and I'll basically kind of let him get on with it as obviously I am not the person with lots of interesting things to say. Perfect, there he is. Yeah, go ahead in your own time, Dieter.
Hi everybody, let me just share my screen. Then let's get started. It's very much a pleasure here for me to be here today and give you a technical dive into Chain Fusion. I'm Dieter Sommer from the DFINITY Foundation, and let's get started now. So the agenda is the following. I'll give you a brief introduction to what Chain Fusion is, and then talk about two core building blocks for Chain Fusion. One is Chain-key ECDSA signing, the other one is HTTP Outcalls. And then talking briefly about Bitcoin integration of ICP. We already had this in a previous talk, so it's a very brief summary and recap, and then going into detail for the Ethereum EVM chain in general integration of ICP. And then give you a brief outlook on what new features are coming up soon, and also talk a bit about what has been done already in terms of projects with this Chain Fusion feature set. But now let's get started with the introduction. So what is Chain Fusion? The problem with blockchains is that per se blockchains are isolated entities. So they per se don't speak to each other, but they are an island. Each of them is an island. And now Chain Fusion intends to bring them together, so to fuse them together, or fuse ICP more concretely with a set of other chains. So fuse ICP with a chain like Bitcoin, Ethereum, and various Ethereum or EVM chains like Ethereum layer 2s like Arbitrum 1, also the Base or the Optimism protocol. And what's coming up in the future is also Solana, and of course there's no limit to what else can be done. But this set of chains shown here will be soon all be available, all but Solana are available already now. And what does this give you? So if you fuse together ICP with other chains, removing the gaps between the chains, so to say, it brings you a single chain dApp experience. So you can implement a dApp on multiple chains, like implement parts of it on ICP, use Bitcoin, use Ethereum, if Ethereum smart contracts, it will have all those things interact with each other. And if done right, it gives you a single chain dApp experience, even though it's a multi-chain dApp implemented using multiple separate blockchains. So in the end, you leverage the good properties of multiple chains in a single dApp. That's the whole point. So you leverage, for example, the low-cost storage and the abundant storage of ICP, the abundant compute of ICP. You can leverage the liquidity of the Bitcoin network, bring Bitcoin over to ICP, for example. You can leverage existing Ethereum smart contracts and utilize those. You can also bring Ethereum liquidity, for example, Ether or USDC or USDT over to the internet computer and use it there for DeFi, for example. So there's no limits to what you can do. This is just a small set of examples. So essentially, we bring ICP's strength to smart contracts on other chains and vice versa. And yeah, as I mentioned already, the networks shown here, all but Solana integrated already. Solana is upcoming. There's still some technology missing for it, but that's coming sooner or later. And of course, in the future, further networks can and will be added as demand will speak. So I would claim Chain Fusion in many ways is the future of blockchain, because blockchain networks become much more valuable the more they are integrated, because they really can leverage the strengths of different networks in a single dApp and are not constrained to an individual network. Now, how does Chain Fusion work at a very high level? So we have two key building blocks and your Canister smart contract logic. What two key building blocks do we need? So the one is securely reading from and writing to other chains of interest. So for example, we need, if to integrate with the Ethereum network, we need to be able to read from the Ethereum network in a secure way and write transactions to this Ethereum network in a secure way. And there are now multiple ways on how you can do this depending on other chains. So for example, for the Bitcoin network, we did a full integration where consensus of the Bitcoin network, like the proof of work consensus, is verified on chain on ICP. This is a very strong, completely trustless way of doing this communication integration. And for EVM chains and Solana, the approach taken is a different one. It's using HTTP outcalls to multiple JSON RPC providers in order to securely or in a decentralized way read from those networks and write back to this network. It's not completely trustless, but it's decentralized. So it's a good compromise solution so that we can get started quickly. There are stronger solutions which may come in the future. Now, this is the first building block. The second building block is signing transactions for other chains of interest. And for this, there's already one protocol suite available. It's Threshold ECDSA, so Threshold Elliptic Curve Digital Signature Algorithm. And Threshold ECDSA allows decentralized signing on ICP without the actual signature private key being known by a single entity, but being shared across around 30 entities. This means it's a decentralized signing protocol. No one controls the key, but the network together controls the key and controls the signing process. This is nice because it's really the most decentralized way of signing you can get. So you can think of it like hardware security, module properties, but realized with a blockchain. And decentralized, so secure and decentralized at the same time. So this is already live and used a lot. And what's upcoming is Threshold Schnorr and EDDSA. This will be also relevant to unlock additional use cases, for example, in the Bitcoin world for ordinals and inscriptions in general, and EDDSA particularly for integration with other chains, like, for example, Solana or Cardano. And with those threshold signature schemes, with those three, virtually all relevant blockchains are supported for the chain fusion technology, which is pretty cool because then we can have a very, very far-reaching way of integrating with other chains and leveraging the properties of the different chains. Now, those were the two key building blocks that we need for chain fusion. Now, there's one more thing, your smart contract, your Canister smart contract logic that implements actually some valuable functionality that you can publish as a dApp or as some new infrastructure service that other people can use. For example, some advanced or cross-chain Oracle or whatever. And once you have those things together, you can build a nice, powerful chain fusion dApp. So much to the introduction. Now, these chain fusion dApps, just to show you graphically, typically they are implemented through a set of canisters on ICP. They hold at least one ECDSA or in the future Schnorr or EDDSA key, and this key is used to derive addresses of other blockchains. Then it can hold tokens of other blockchains and call sign and send transactions to other blockchains, for example, to the Bitcoin network, to the Ethereum network, to Solana, and so on. And really, we can split now the logic and storage between ICP and other networks, leverage the liquidity from other networks, leverage available smart contracts from other networks, and so on. So it's really very, very nice what we can do here. And now, after this brief introduction, let me go now into the first key building block, Chain-key ECDSA signing. So Chain-key ECDSA signing is a suite of protocols to realize threshold ECDSA signing, which enables canisters to have ECDSA keys and sign with those keys. So this is really crucial. So to show it graphically here, a canister smart contract on ICP now can have an ECDSA key. And with this ECDSA key, it can sign transactions to other blockchain networks. And with the upcoming Schnorr and EDDSA, essentially all other blockchain networks are supported from the cryptographic point of view. Now, looking a bit deeper how this is realized, of course, the canister itself does not hold the private key because this would not be secure, but it controls the private key in some way. So how it's working is that there is a threshold ECDSA subnet, and this has around 30 nodes, and each node has a key share for some threshold ECDSA key. And together, the nodes of this, so there are only 4 shown here, it's around 30, I think it's 28 exactly. Together, those nodes can compute threshold ECDSA signatures. And only if a certain minimum number of nodes participate, those signatures can be computed, and a smaller set of nodes does not have a single bit of information of the private key, even if they put together their shares. So this is the nice part about threshold cryptography. Only once you reach a threshold of nodes, then you can create signatures or reconstruct the key, which is of course never done. And now we have an API that's very simple. So some client canister here that wants to use the threshold ECDSA protocol suite can on the one hand obtain a public key, like it calls the function ECDSA public key on the management canister locally. What this means is it's then getting routed over to some subnet that holds the corresponding threshold ECDSA key, like a large high replication subnet. And then this subnet sends back the public key. The public key is no problem to be seen by the canister because it's public information. And the private key, as I said before, is never leaving this subnet here. So it's represented in the form of the key shares here. But what the canister can do, it can request a signature with their private key from this subnet. And if it requests this by calling the sign with ECDSA method on the management canister with the according parameters, then this subnet would compute the threshold ECDSA signature using cryptographic multi-party computation protocol. And this takes a couple of rounds of ICPs, it takes a couple of seconds, and then it returns a signature as requested by the canister. And of course, only a canister to whom a key belongs can request a signature for it. So this is advanced cryptographic multi-party computation, and this makes this very decentralized and secure. Now let's go a bit more into details about keys that the canister controls. So I was talking about one key. So this key that Secret shared here, this is actually a threshold ECDSA master key. The master key, there's only one of them. Actually, it's replicated on 2 subnets currently, but it's the same key. And this is now represented through this key here on the left side, this master key here. And now every canister has a so-called derived key. So it's a key derived at the level 0 of a derivation hierarchy. This means every canister gets a derived key, and the canister principal is used as a string for the key derivation. So there's some hashing involved here to derive a new key from the principal that is presented here. And now let's say this is the key for our canister we've been talking about. So this is then the canister root key. There's one of those per canister. And now the canister can either use this canister root key if it only needs one key, or it can use further levels of the derivation hierarchy here. So there's 255 levels here in addition to the first level, so 256 levels in total. And these 255 levels here, starting from the canister root key, are controlled by the canister themselves. So the canister can now, for every operation of getting a public key or having a signature with the underlying private key, can specify a further derivation hierarchy to point to any key here in this 255 levels deep hierarchy. Let's say, for example, we want to have this level 2 key here, for example. Then they could either specify a string as a blob here to specify the derivation, or a 32-bit, so 4-byte large integer. So this is BIP32 respectively, a generalization of BIP32, from the Bitcoin world to derive keys. And this key, for example, would be derived by passing over 2 blobs, respectively 32-bit integers, and those would specify, the first blob would specify this key and the second one this key, and then we would arrive with the derivation to this key here, and this could be used for an application. So with this derivation path, the public key can be obtained, or a signature with the private key can be made. And there are quadrillions of keys per level, so there's no shortage of keys. Now let's have a bit more detailed look at the API of Chain-key ECDSA signing. So there's these 2 functions I already mentioned, ECDSA public key and sign with ECDSA. Let's look at the left one first. So ECDSA public key has 3 parameters. So first, the canister ID. This is optional. If it's left out, the calling canister is assumed for the canister ID. The second one is the derivation path. that defines the path here to which key we want to get. So this is this vector of blobs, or vector, each blob can be in the BIP32 case just a 4-byte integer. And this specifies more or less a pointer to which key we are talking about. So with this vector of blobs, you can point to the key you want to have. And then for the key ID, so this refers to the master key. This needs to present a curve. Currently, there's only the SEC P256K1, this Bitcoin curve, so to say, available. And then we need to specify whether we want to use the test key or the production key. So the test key is called test key 1. The production key is called key 1 for the deployed ECDSA key. And that's already it for the ECDSA public key. So that's simple interface. And sign with ECDSA is equally simple. So how this works is you pass along a message hash, which is a 32-byte hash of the message you want to sign as a blob. You have the same way of specifying a derivation path, and you have the same way of specifying a key ID as for the ECDSA public key method. And then you get a signature back with the public key specified through the derivation path and the according master key you specify. Here is some more information that's for reference. You will get the slides later. Yeah, so it summarizes all the important things you need to know about this method. And now, armed with this threshold ECDSA mechanism, canisters can do very powerful things. Namely, they can control ECDSA keys. They can derive addresses in other blockchains from these keys, and then use the underlying private keys to sign transactions. So for example, they can sign now transactions for the Bitcoin network, receive funds on the Bitcoin network, receive funds on the Ethereum network, sign transactions, and so on. So all supported networks now are supported with this cryptographic primitive, which is very, very powerful. And as I mentioned already, besides threshold ECDSA, soon there will be threshold Schnorr and threshold EDDSA available to cover, from a cryptographic perspective, all other, or essentially all other relevant chains out there for the integration. So much to threshold ECDSA. Next, let's talk about HTTP outcalls. This is another building block that's used heavily currently for the Ethereum and EVM chain, and then also for the Solana network integration. So Canister smart contracts, in a nutshell, can interact with Web2. So from a Canister perspective, it looks like it can make an HTTPS call to a Web2 service, even though this is replicated computation sitting on a blockchain, and this is a centralized single machine. And yeah, from a conceptual perspective, it's making a call to this HTTP server and getting back a response. So under the hood, it's a bit more complicated. Let's look under the hood a bit. So what happens if a canister makes this HTTP call? It's called an outcall. So what's happening is it talks to the management canister on the subnet, and then every replica, so every node machine of the subnet, makes the same call to the specified server. So in this case, we show 4 replicas. They all make the same call. The server responds to all of them, and some may also fail. So for example, one here, one request is not getting a response, but 3 are getting a response. Responses might be a bit different. So for example, they might contain things like timestamps that are different. They might contain session identifiers, sequence numbers, and so on. So those things must be removed. So there's some transformation function applied that the program of the canister must specify. This transformation function is applied by all the replicas. And what comes out of the transformation function is supposed to be the same in all the responses. So this is the rule after which the transformation function must be built. And then those transformed responses go through consensus. And if everything works well, there will be consensus by at least 2/3, so a supermajority of the nodes in the subnet, like in this shown example. And then the response, there's a single response coming back to the canister. And that's, in a nutshell, how those HTTP outcalls work. So this is a pretty powerful feature. They have a trustless integration of the internet commuter with the Web2 world, and this is now used, as I will show later, for the Ethereum and EVM integration. But now let's get to a bit different topic. So the first use case the internet commuter has created for chain fusion, like I think that was already 2 years ago or so, the Bitcoin ICP integration. How did that work? So let's look at the Bitcoin integration first, and then an important use case. So the integration of ICP with Bitcoin is a bridgeless and trustless integration of the internet computer with the Bitcoin network that brings smart contracts to Bitcoin. Because Bitcoin itself does not have smart contracts, by this integration, we can use ICP smart contracts to give smart contracts to the Bitcoin network, essentially. And it uses Chain-key ECDSA, as I explained before, as a building block. It does not use HTTP outcalls, but it uses a even stronger mechanism, namely a direct integration at the network level and validating Bitcoin's consensus on-chain on ICP. In a nutshell, how this works is that the Internet Computer Protocol stack was extended with some Bitcoin functionality, and one subnet of the Internet Computer was enabled with this Bitcoin integration functionality. And this leads to a situation that this subnet starts up a so-called Bitcoin adapter on each of its replicas. And this Bitcoin adapter connects to the Bitcoin network. So each adapter on one replica connects to multiple nodes of the Bitcoin network. And then whenever a block in the Bitcoin network is mined, the block is sent to each of those adapters, and those blocks are then passed up through consensus to a Bitcoin canister. So this Bitcoin canister is a ICP smart contract implemented in Rust, and this canister receives all the Bitcoin network blocks. So all the blocks from the beginning of the Bitcoin network were fed into this canister, and in every block, the UTXOs, so the unspent transaction outputs of the Bitcoin network, are analyzed, and effectively the spent UTXOs are removed from the state, and the new created UTXOs are added to the state of the Bitcoin canister. And essentially, the Bitcoin canister just tracks the set of UTXOs that's valid at a given Bitcoin block. And this is very powerful because now any canister on the internet computer, be it on the same or a different subnet, can make queries and ask this Bitcoin canister about which UTXOs a given Bitcoin address has. And with this, you can determine the balance of this Bitcoin address, and you can determine the UTXOs themselves and use them to, for example, craft a transaction if these UTXOs belong to the canister, and then send a transaction back to the Bitcoin network. So that's also supported by the communication level integration here. So this whole thing is like a Bitcoin node that's running on-chain on ICP that verifies the proof of work of the Bitcoin network and keeps track of all the UTXOs in the Bitcoin network and allows any canister to query those UTXOs, so query addresses for their UTXOs. So this is very powerful because it's completely trustless. There's no additional entity involved. It integrates directly with the Bitcoin network, and it validates the proof of work part of the consensus of the Bitcoin network on-chain on ICP. So that's the native Bitcoin integration, the technical part thereof for the communication and integration of the networks. And now using threshold ECDSA, this Bitcoin canister can also sign transactions to the Bitcoin network, or some canister that uses the Bitcoin canister can sign transactions to the Bitcoin network and submit them through the Bitcoin network to the Bitcoin canister back to the Bitcoin network. So this way we have essentially canisters that can act like normal users on the Bitcoin network. They can have a Bitcoin address thanks to the threshold ECDSA keys. They can receive Bitcoin on the Bitcoin network. They can send Bitcoin because they can craft transactions and submit them to the Bitcoin network via the canister here. So this is a very powerful integration. It's completely trustless, completely decentralized. Some more explanation for reference. So one interesting part is that the Bitcoin canister is probably one of the largest smart contracts in the world. It has, I think, something like 60 or plus gigabyte of storage currently that it consumes to track all the Bitcoin UTXOs, including all the indices on them. Now there's been one powerful application built by DFINITY. Many other people built other applications, but one has been built by DFINITY, which is the ckBTC, the Chain-key Bitcoin application that sits or that builds on top of this Bitcoin integration. Now, Chain-key Bitcoin is a Bitcoin twin token on the internet computer, which is 100% backed with real Bitcoin, which is held in custody by a smart contract on ICP. And it uses this Chain-key ECDSA signing that I explained before, and this native Bitcoin integration I explained just now as its building blocks. Now let's look at it in a bit more detail. So here is the Bitcoin network. Here is one subnet of ICP where we have a ckBTC minter. So this is the more or less the brain of this Bitcoin, the ckBTC token, and then we have the ckBTC ledger. That's just the ledger that manages the ckBTC. So how it works, that any user who owns Bitcoin can transfer Bitcoin to a specific address on this ckBTC minter. And the minter then waits for enough confirmations on the Bitcoin network. I think it's currently 2 hours. It will be reduced to 1 hour if I'm not mistaken. So 6 confirmations. And then this canister locks up those received Bitcoins. And once it has enough confirmations to be sure that there's no reorg on the Bitcoin network, it mints a twin token, the ckBTC token, on the ckBTC ledger. And this is minted to the person that's specified in the transaction by the person who sends the Bitcoin over. Typically, the person who sends the Bitcoin is the beneficiary of those ckBTC. And then once the ckBTC is in this ledger, it's just a normal ICRC1 token, so supporting ICRC1, 2, and Zone 3. And it manages, this ledger manages ckBTC as a regular ledger on the internet computer, and every ckBTC token is backed 100% by Bitcoin locked up in this minter. That's the important part. So there's 100% backing here that can be publicly verified. That's also the important part. And now users and canisters alike can use this ledger to transfer ckBTC. And they make just the normal calls according to the ICRC1-2 interface to, for example, ask for a balance, making transfer, or using the ICRC2 approved transfer from mechanism to transfer or give approvals to other people to pull funds from their accounts. And that's a very powerful thing because ckBTC transfers are very, very cheap. It costs a cent or even less per transaction compared to multiple dollars per transaction if you do it directly in the Bitcoin network. And of course, if you own some ckBTC, you can anytime if you want, because it's backed by real Bitcoin, you can have underlying real Bitcoin back on the Bitcoin network. Whenever you want, you can do that. So much to this. Next, so it was just a brief excursion to the Bitcoin discussion. Now let's go into Ethereum and EVM chains and their integration with ICP. So there's one endgame scenario for an Ethereum integration, which is a completely bridgeless, trustless integration. This architecture is based on running full Ethereum nodes like consensus and execution node each on each of the node machines on one subnet, and then having these Ethereum nodes sync their state with the Ethereum network, and then use queries using HTTP outcalls to the local host here, to the respective local host, to make queries to these co-located nodes, and then sanitize the results back through consensus. And this is very, very powerful because it behaves very similarly to an on-chain Ethereum node that would sit on-chain, but it's really sitting on the node machines, and consensus is used to emulate an on-chain Ethereum node. This is quite a big project. That's why it's deferred to future work. And what has been done to be more quick to market is the following, namely an EVM RPC Canister based approach. Let's look at this one. So this is already deployed and can be used and is already used by people. So an EVM RPC Canister. So this canister here, it provides an on-chain JSON RPC API, or respectively also an abstracted RPC API using Candid formulation on-chain on ICP. And this is for Ethereum and EVM chains. So you can reach multiple chains with this canister. And how it works is that this canister connects to so-called JSON RPC providers, like for example, Alchemy or Anchor, Public Node, Cloudflare, and so on. And this works in a way that it uses HTTP outcalls. For example, if the client canister wants to query, to make some RPC call, so this EVM RPC canister queries 3 different of those providers, and only if they all give the same result, as a response flagged as valid is given back to the client canister. And overall, we've currently 5 different public RPC providers integrated. I mean, those 5 here, and depending on which network you're interacting with, you get 3 of them. You get the responses, a consensus over 3 of the responses back to a client canister. So, for example, if you talk to Ethereum, you get back a sanitized response from 3 of those providers. If you talk to some layer 2 that might have different support here, you get the EVM RPC canister talks to 3 of the different providers. And if you want, you can also specify to talk to more providers if you want more security. And then it's a pretty secure approach. It's not trustless because you still need to trust that not all of them are lying to the EVM RPC canister. But it's a good middle ground, and it was relatively fast to build this solution and to bring it to market. And now we have an EVM RPC API on-chain that can be used by anybody. It charges cycles for its use because it needs to pay for the HTTP outcalls that are being used. And it needs to also have API keys of some providers that are not completely publicly available. And these also cost money and need to be managed. So much to this. Which chains are supported? So those providers here that we have integrated support overall currently those 4 chains: Ethereum, Arbitrum1, Base, and Optimism. And more chains can be easily supported by the user bringing their own RPC provider and API key and specifying them. And the user can even deploy their own RPC canister, like fork the code and even change it if they want to. So there's no limit on how this can be used. I'll go into some more detail about this a bit later. Now, first, let's talk about bringing your own RPC provider and API key. So, for example, if the user does, for some reason, want different RPC providers, for example, they trust those more, like, for example, Infura, GetBlock, Gateway, FM, or if those providers or other providers allow the user to access different blockchains that are not accessible through the other providers, then the user can use those different providers. What they need to do is to either use a provider that's completely open and publicly available, or they need to obtain an API key from those providers and then provide this API key and URL information of this provider with their call, and that's essentially it. So reasons are really mainly to use your own API, RPC providers and API keys. The reasons are to integrate with networks not supported by the default providers shown before. The trust model, like if you want different or additional RPC providers or more RPC providers that should be queried. If you want a guaranteed quota by using your own API key that's not shared with other people, because otherwise the API key for the default provider is, of course, shared with all the users that access this canister. And cost. So then you might have a provider that's cheaper. You might even have a call out to your own provider if you want to. So any RPC provider that's now compatible with the Ethereum JSON RPC spec should work with this approach. So that's pretty powerful because it can give us a wide range of integratable chains. And essentially every EVM chain that has a provider should work. So we haven't tested all of them, but should work. And if you run into problems, please create an issue in the GitHub repository for the RPC canister so that we can look at it. And yeah, this gives you now a very, very powerful way to integrate with EVM chains that are not part of the default setup. So it's a very, very broad-based way to integrate with other chains. So next up is deployment options. So this Ethereum RPC canister has 2 deployment options for it. So one is to use the shared RPC canister that's available on mainnet and controlled by the NNS. I gave you the principle here and the candidate devs and the WASM link of the so that's the latest ones. And this canister runs on a fiduciary, so on a large high replication subnet, and it can be accessed by any canister on the internet computer. And you just call it like any other canister. So that's very easy to use. And it's the default way we envision people to use the RPC canister. So just attach some cycles to your call, make the call you want to do to this RPC canister, and get information from a blockchain you want to connect with. So it's really easy. There's a couple of supported networks. There's 5 supported RPC providers currently. More may be added in the future. Currently it's these 5. And if you want, you can bring your own API key and just specify this API key and the URL of the RPC provider in the request, and then the canister uses this. So it's really a ready-to-go solution that's very powerful already. And if this is not enough for you, so you have more specific requirements, you can deploy your own RPC canister on mainnet. So you can just fork this RPC canister, you can deploy it verbatim, or you can just modify it also if you want to, for example, do whatever modifications that your specific use case requires. So it's really, there's no limit to what you can do with this approach, but of course, it's much more higher maintenance, more effort to do initially, and you need to keep the thing, or your DAO, or the DAO of your dApp needs to keep this canister also up to date and maintain it. So it's a much higher effort solution that can be useful if you have more specific needs than more specific requirements than what the shared RPC canister on mainnet allows for. So you can change the code, you can fine tune everything as you wish, and of course you can register any RPC provider and API key and access it without all the time with every request specify the API key and the provider URL. So it's more convenient to use if you have this requirement. Now let's have an overview of the API of this RPC canister. So this RPC canister has 2 ways of calling Ethereum RPC functions. And one is using candid method. So 6 RPC calls have been modeled as very convenient to use candid methods, which have a candid type and are not JSON, but really you have everything expressed as in a typed way. The methods supported are ETH fee history, ETH get logs, ETH get block by number, ETH get transaction count, ETH get transaction receipt, and ETH send raw transaction. We think that with those you can get already quite far, and you can build lots of integrations already. And the nice thing is that they are really convenient because lots of heavy lifting is done behind the scenes. So for example, whenever you call one of those methods, then 3 RPC providers are contacted with the same request, and only if they all have the same response, then you get back an okay, a valid response, and otherwise you get a flag that the response is invalid. You still get back the individual responses of the 3 called RPC providers. And also it handles already some technicalities, like for example, specificities of the representation and canonicalization requirements for different RPC calls, which have been already accounted for in the canister, which you would need to do manually if you use the approach here of using a generic request method. So whenever you can use one of those things, if they're not sufficient, you need to revert to the generic request method shown here on the right side. So this is more low level. So essentially it exposes one method, which is request. And this is essentially making a JSON RPC request to one specific RPC provider. So it's harder to use because if you want to query multiple RPC providers to be sure that no one is lying to you, or not all of them are lying to you, you need to do this manually, and you need to manually also potentially account for differences in the canonicalization of the JSON responses and check whether the canonicalized responses of the different called RPC providers are the same. So you need to do some more heavy lifting, which is done by the RPC canister on the left side here. You need to manually when you use the request method here on the right side. But it gives you access to more functions, like ETH call might be something very valuable you want to need for certain integrations. ETH get transaction is another one, and ETH get balance might be another one that's very important. But yeah, ETH call is maybe one of the most prominent things you might want to do with this function here. And also over time, more functions might be exposed with the candid API. So this is now an MVP, a minimum viable product that you want to get to market quickly. And therefore, it doesn't expose all, but only an important subset of the methods as JSON methods here. Yeah, and what you cannot get done with the candid methods, you can get done with the request method. So essentially, with this request method, you have an on-chain, you have a full on-chain JSON RPC provider on the internet computer that you can talk to. So it's very powerful. Now, a bit more detail about the API. So the candid methods we saw before on the left side have a very simple API pattern. So all of the methods have the same pattern. Let's look at one example here, ETH get logs. They accept an RPC services, plural, then an optional RPC config, and depending on the method here, a specific arguments like the get logs args here for this one. Then there's a specific response per method coming back, like here the multi get logs result. Multi here alludes to that multiple RPC providers are called, and there is some more metadata about whether they all were saying the same, and we have consensus on their responses. So now those three inputs here, the RPC services, the opt RPC config, and the RPC request arguments, those are actually very simple. So the RPC service here, the first one, is a variant of the different networks we have, like ETH mainnet, ETH Sepolia testnet, and Arbitrum 1, and so on. Or custom, and custom is where you can just specify your own chain ID, and the service is to call as a vector of RPC API, which is here specified on the right side. So this RPC API is just the URL of the RPC provider to call, plus the headers optionally, if the API key needs to be specified as a header. If it can be specified as the URL, it's just part of the URL for the with which you call the RPC provider. And yeah, if you use a non-custom thing, like you can just use ETH mainnet without anything else, then the canister itself chooses 3 applicable RPC providers, but you can, for example, choose ETH mainnet and choose on your own which ETH mainnet services you want. So one of the 3 of those 5, for example, you could choose if they support ETH mainnet, and yeah, then we have a very flexible way. So you can, for example, say you want Alchemy, BlockBuy, and Cloudflare, and you can specify this here. Or you can just leave it to the canister and just say you want ETH mainnet and specify nothing else. Then you get a choice of 3 RPC providers that's chosen by the canister. So much to how to specify the service, either predefined things or custom. And now the RPC config is a very low level thing, but I still mention it. So what you can specify here is a response size estimate. This is not for correctness, but that's for minimizing cycle cost of the call. Because the HTTP outcalls, I did not mention this when I gave an overview. So there you need to specify the maximum response size of the response, and this is charged in terms of response. This is a technical limitation why this is the case. And if you know that your response size is for sure below a certain size, then you can just specify this here. If you don't specify it, the canister for those candid methods here already takes a very reasonable default. So it doesn't use the maximum, but a very reasonable default. And if the default or the specified size is too low for some reason, then it retries with doubling the size until it works or until there are no cycles left in your call. So this way, it's very easy to use and still good for cutting down the cost. So it's a good compromise between those 2 things, how this is implemented at the API level and from the semantics of the RPC canister. So it's easy to use. If you don't care to optimize completely, you just ignore this response size. And if you know your response sizes, then you can specify it and maybe cut down the cycle cost a bit more compared to what the defaults would give you. So much to the candid methods API pattern. Let's next come to the request method. So the more generic request method and how the API pattern looks there. It's actually very similar. We have also an API service, this time singular, because only one, because it does not automatically call multiple and make consensus over those 3, but you have to do this in your client canister. Next, there's the JSON. So the JSON is just the JSON request as text. So there's no There's no structured data structure here, but it's really just JSON, like when you would use a normal JSON RPC API on Web 2. And there's the max response byte, similar to what's in the RPC config here. So here, the RPC service similar to this, but you only can specify a single thing, like ETH mainnet means ETH mainnet service, not the vector thereof. And the same for the others. And then you can also have a custom thing. It's again an RPC API like here, but not the vector, but just a single one. So it's again the URL and the optional headers for specifying the API key if necessary. And then the max response bytes is exactly the same as here. And yeah, again, use it if you want to cut down cycle consumption as much as you can. Okay, yeah, so much to the API. So I tried to summarize the key parts of the API here so that you can get a quick overview when looking through the slides later on also. And the details are in the corresponding candid file. So now the Ethereum RPC Canister, as I mentioned already, allows you to register and manage your own RPC providers if you deploy it yourself. For the NNS managed one, only the NNS can do that, can add and manage the RPC providers. Now, if you deploy your own one, what you can do is you can register an RPC provider. So use the function register provider. You need to be authorized to do that. I'll explain shortly how this works. And once you have registered a provider, for example, you can register Infura or whatever else you want. And then you have it available as one of the pre-registered providers. You can also query register providers to get the provider ID. Then this ID you can use to update the register provider, for example, to change the API key if you rotate the key, for example. And yeah, in order to call those functions, you need to authorize a principal to do so. And this authorization is done by the controller. So the controller calls the authorize method and can pass on the principal and the method that can be called by this principal. And by this can define an access control policy for the different methods here. So I don't go into any of the details here. The documentation talks about this. So all of those things you need to take care about when deploying your own RPC canister. So my recommendation would be only do this if you really cannot use, or if you really have strong reasons to not use the public NNS controlled RPC canister, then deploy your own one. Otherwise, just use the public one. It's usually much simpler than rolling it on your own. So much to this. Now, one important use case that has been built for the Ethereum and EVM integration is the ckETH and ckERC20. So what is that? This is analogous to ckBitcoin, but just for Ether and Chain-key ERC20 tokens. So ckETH and ckERC20 are Ether and ckERC20 twin tokens on the internet computer. They are 100% backed with real Ether or the respective ERC20 tokens, which are again, like for Bitcoin, held in custody by a smart contract. And like for Bitcoin, it uses the Chain-key ECDSA signing, like the threshold ECDSA signing specifically. And it uses this RPC-based Ethereum integration as building blocks. So one minor comment here, so it does not yet use the EVM RPC canister, because those two things, the canister and the ckETH, so the ERC20, they were implemented in parallel, so it couldn't use the canister yet, but it implemented this functionality on its own, and it will switch over as upcoming work. So this is a work item that people in the team are tackling soon, I think. They're switching over to using the EVM RPC canister from the ckETH and ckERC20. Now, to visualize how this works, very similar or conceptually exactly the same way as ckBTC works. So let's here display the Ethereum network using this, I don't show it here, the RPC canister in the future. Now directly the minter here, the ckETH ERC20 minter, can receive, for example, Ethereum or USDC currently. Then it locks those tokens up and mints after enough confirmations on the Ethereum network. So once we have finality here, then it mints either the ckETH or the ckUSDC on the respective ledger. So there's one ckETH ledger and there's one separate ledger for each ckERC20 token. Currently, there's only one, namely ckUSDC deployed as far as I know, but with NNS proposals, further ERC20 tokens can be deployed, and each ERC20 token then gets its own ledger and also its own archives, and so the whole ledger suite of canisters. I haven't shown those details here. And now, once we have those tokens, so once users have brought some tokens over, users and canisters can just talk to the ledger, like the ckETH ledger here, or the ckUSDC ledger, and transfer tokens for a very, very low fee on the internet computer with very fast finality. So that's the nice thing about it: low fee, fast finality, and on-chain on ICP. That's really cool. So we bring over liquidity from the Ethereum network here, which is very important for DEXs and DeFi use cases and other use cases. So much to this use case of chain fusion in the context of Ethereum and EVM chains. Now let me give a very brief outlook what's upcoming. So there's a couple of exciting things upcoming. Threshold Schnorr is one of them. Threshold Schnorr will unlock the issuing of inscriptions on the Bitcoin network using the Schnorr signature scheme. Currently, this cannot be done fully on-chain. This is coming soon. Then on-chain Bitcoin block headers. This is important to access the areas where the inscriptions are stored. This is currently not on-chain yet, but with the block headers, you can have this in a fully trustless way also on-chain. And then you can have the Bitcoin inscription indexing part also on-chain, which is very powerful. So no other blockchain will be able to offer this in the near future. And then at the cryptographic front, there's also threshold ECDSA coming on the Edwards 25519 curve. This enables the cryptographic integration with blockchains, which are based on ECDSA for signing transactions. And there's a couple of them, like for example, Solana, Cardano, Stellar, Elrond, Algorand, and so on. So there's a few of those, and all of those become available from the cryptographic perspective once this feature is rolled out. But important note here, of course, there's still an integration for the bidirectional secure communication required for each of those chains that we want to access. This could be done like with an RPC canister, as mentioned for Ethereum. This can be done with a light client if people want to do so, or any other suitable method. So anyone can build this themselves. This does not need to be done by the foundation. Anybody can build this, deploy it, as long as it's buildable as only smart contracts and doesn't require platform changes on the internet computer. Now, a couple of example dApps that have been built using chain fusion technology. As I mentioned in this talk, ckBTC, ckETH, ckERC20 have been built by the foundation. The OASI multi-chain wallet has been built by the foundation, or is being built. Then the Orbit institutional wallet is being built. There's the Bionic Ordinals marketplace that's being built. It will benefit also from the Schnorr scheme that's coming up and from the Bitcoin block headers that will be available on chain. Then the Orally Oracle network builds heavily on chain fusion tech. Helix market does so. It's one of the biggest users of threshold signatures. And then there's NFID vaults, an omni-chain multi-sig smart wallet protocol, which is also building on chain fusion technology. And there are probably many more. I just picked some examples that are around. And this is also what I would like to conclude with. And now I think it's time to enter the question round. We have still 5 minutes for questions.
Thank you so much. That was really, really great. I can see that Matthias has asked a few questions. I think given we've only got 5 minutes, maybe it makes sense to prioritize the 2 most recent ones. And then guys, if you've got any other questions, we can get onto those. So first of all, Matthias asks, would it be feasible to customize an RPC canister, deploy your own, to the point of turning it into an indexer for my dApps requirements?
So when you customize the RPC canister, when you deploy your own, you can do anything, right? I mean, you can just fork the code and then do whatever you want.
Cool. And then his other question here is, how would IC handle the scenario where USDC is coming in from both ETH and say Solana? Does be managed only in the ckUSDC canister? So
I think it's something we should avoid because it will lead to fragmentation. So in my view, this would probably, I mean, you can implement things in different ways, but as far as I understand it, the current way of how it's implemented would mean it's would be 2 different tokens. So it would lead to fragmentation of liquidity. So it's better to have one USDC probably. Of course, technically you can do it that you merge them together, but this would require this functionality to be implemented in the mint, like to consider that one token can come over from both chains. but currently it's each token is mapped to one other chain. So that's something that would be an extension if you want to have USDC, ckUSDC from multiple chains in a single CK ledger.
Great, thank you so much. Oh, I can see Matthias is typing. We have 2 minutes left, so Matthias, if you have any final remaining burning questions, I know we had to skip a couple, but if any of them are very pressing, or guys, everybody else that's around at the moment, do say if you've got anything to ask. Looks like that isn't for now, so I will just say thank you very much there we go, one more question from Matthias.
Yeah, so can ICP become an execution layer for any chain using only the target chain's assets? So essentially, yes. So I mean, you can say it's a co-processor. You can build a co-processor on ICP. For example, you could have an Ethereum contract that outsources heavy computation and storage into ICP, and then you can have a chain fusion dApp where the heavy lifting is done on ICP and where some parts of the dApp are still on Ethereum, for example, where you want to have the 1 million nodes for replication. So you can really pick and choose which properties of chains you want to use for certain parts of the functionalities of a dApp. That's the main idea. You really pick and choose the best functionalities of chains that are supported and then build your dApp that way that you have the best features of every chain comprise the overall functionality of a dApp.
Cool, excellent. Well, thank you so much, Dieter, for taking the time today to run this workshop. It really seems like people enjoyed it, and obviously lots and lots of questions, especially from Matthias. So yes, thank you very much. And I think it was asked at some point, just to clarify, we will put these recordings up on YouTube, so they will be accessible to you. And yeah, in the meantime, see you guys at the next one. Thank you so much, and have a lovely evening. Bye-bye.
Thanks, everybody. Goodbye.